Alright, so you might have seen me in the high frequency section before lunch. This is now the corresponding low frequency section. Again, similar idea, but we're also covering the Twin Builder project. So if you're looking on your schedule for this afternoon, you'll find there is a digital twin presentation after this in the other room, and that uses the technology inside digital twin along with the PDC products. So if we start off with TDM, this has kind of been, I think I worked out it was a 5-year journey for ANSYS to take their technology for solving motors. So it used to be an extremely painful process to solve a motor in 3D in ANSYS. But since then, we've kind of ticked all the buttons, meshing is better, geometry is better, and solving is better. So to give you an example of just the solver technology for now, we now have something called time domain decomposition solver. It was released in beta format in R16, I believe it was. And the idea here is that we can take sequential time steps in a time domain solve, and we can lump them all together into one matrix and solve it in one big hit. The idea behind this is we want to get around scaling issues. So if we use the standard transient solver even in 2019, for a 2D solve, usually 3 or 4 cores is where we start to run out of scaling. With 3D, we sort of 8 cores, maybe 10 cores and starts to run out. If we can use TDM, then that number goes straight out the window. If you use 2D, you can scale to 128 cores if you like. Here's an example of using a 3D one. This is a fairly enormous model with almost 1 million tests, and we solve 1,000 time steps. So if we look at this using the old-fashioned method, it's 270 hours, which I think is about 12 days. If we keep throwing more and more cores at it, by the time we hit 400 cores, we're down to just under 5 hours. So it's a method that, no matter how big the problem is, this is a method where you can just throw horsepower at it and it will solve it faster and faster each time. So we look at some of the enhancements in this release. This is the first time we've ever been able to do what we call periodic TDM with induction machines. So a lot of the work we do is revolving around optimization workflows, and for that we want to be able to solve a transient problem until it reaches steady state, and then record the average torque and the average powers and look at the waveforms in the steady state. And so periodic TDM will slice up your simulation into one electrical cycle, and it will solve that same electrical cycle over and over until it converges. So with induction machines, though, the rotor has a different set of frequencies that are exciting. And so usually that means you can't use TDM with it, periodic TDM. So 2019 R2 is the first time where we've been able to use induction machines with periodic TDM in certain scenarios, specifically for the efficiency map generation. We also have half periodic TDM for permanent magnet machines. So now rather than solving a full electrical cycle, we solve the first half and then we just mirror it onto the second. And so in practice, this is a full 3D model of a permanent magnet generator. Usually it needs 330 gigs of RAM, now it needs 190. Same with CPU time is hard to get. So this is a very simple implement. You just turn the box on and cut the simulation time in half, and that's how you get that 2 times speed up. For a lot of very complicated 3D solves, we find there is a startup region to the motor workflow, and then there's another part where we want to actually do some serious analysis. So an example of this is when we want to look at exciting induction machines with PWM cycles. Usually if you want to use pulse width modulation with an induction machine, you've got to wait a very long time for the machine to settle down before you can start getting good data out of it. So what we can do now is you can make 2 copies of your design. You excite the first design with a sinusoid, which you can use very long time steps with, and you jump forward until it's at steady state, and then you use that to seed the second design, and you can put whatever excitation you like in. So you can shrink the time steps right down, and you can keep iterating through this part without having to come back to the startup phase each time. So for 3D motors in particular, that's a fairly enormous saving. And it works well for permanent magnet machines as well. If we look at motion, particularly with the push towards having magnetic gearboxes in motors now, we can have as many different types of motion as we like in a single 3D simulation. So we used to be limited to, say, just having rotation or just having translation in a model. You can now have whatever combination you like. And so that means for designs like this, you can have your motor setup in the center, and then your stationary element, your gearbox, and then a different motion band setup running outside for the gearbox output. And there's no extra work to get that to function. Particularly for people who do a lot of material modeling, you can now have temperature-dependent BH curves. So previously, you'd have to pick the one you thought it would be at, right? And if there was local heating, then those elements wouldn't adjust properly. So now you can put in a sequence of curves, and then as there's local heating of this material as it passes through the eddy current meter, then each element by itself pulls out a different BH curve depending on what it should be, and interpolates as necessary. And that works for all the solvers. We had a previous limitation with the solver where when you do very, very large 3D eddy current solve, so it might be a wireless charging for a car where you've got a large section of the car included, or it could be induction machines as a seed design. You found that once you hit sort of 10 million elements in size, you just gave up. There was no real way to get beyond that hard limit. It wasn't solver hardware limited, it wasn't RAM limited, just solver just wouldn't go any higher. So at R1, so early at the start of the year, they kind of got rid of the limitation, but then the scaling was a bit mediocre. At R2, we have now borrowed the domain decomposition solver from HSS, and it means that you can scale the solver up now. So it used to be limited to 10 cores, now you can throw 80 cores out if you want it in order to get that nice scaling north of 20 million elements. So that's kind of the solver part. The other half of the last 5 years has been implementing a modification to our meshing algorithm. So if you've ever done any generic 3D work, particularly with CAD, you'll have used what we call our tower mesher. That's very good for representing this sort of scale geometry. But specifically for rotating machines, we really want a very consistent geometry. If you've used ANSYS meshing, you'd call it a structured mesh. And so that's what we're trying to build here, but we don't want to change the fundamental towel meshing because it's what we use for everything. So clone meshing is an option you turn on. And the idea being that if we compare two examples, this is without clone meshing and then this is with it. This uses more elements than this one does, and yet it still gets a very ugly torque ripple on it. And we can't really pull out harmonics from this for any sort of simulation. But because now we've structured the elements, both in the stator and the rotor, it's very easy to pull out a nice realistic torque ripple. This is excellent for doing harmonic and acoustics analysis as well. So the last sort of piece of the puzzle for this algorithm, which we've only just got this year, is the ability to locally control the way it builds up each segment of mesh. So it used to be that the only way to control the elements in this part was you set the angle that it would make along each curve face and how far it could go before it created a new aspect ratio element. Now you've got the option to choose wherever you like. There's a tool called the clone mesh density control, and you can apply it anywhere in the model, and it gives you complete control over what size elements you have in any bit of geometry separately. It also gives you the ability to control the number of elements and the depth as well. This used to be in particular a very frustrating exercise to get it to work. If anyone's been doing strongly focused on the way that we do magnets and tips of rotors, you'll have come up with your own set of hacks in order to get these really thin layers of elements around the band. We used to do all sorts of things like create custom sheets and mesh them with segments and all that. Now all that's gone. You can leave the edge of the band as a perfect cylinder. You no longer need to segment it. And the other thing you've got is an extra 2 options here, which allow you to choose how many layers you'd like on each side. So if we take this tip in particular, there's an edge cut mesh, which I'll discuss in a minute. But there's also this ability to add as many layers as you want. And it will just look for the tip and the band and the rotor and insert them automatically. So it works flawlessly, basically every single time. The last thing is for people who do a lot of work with loss modeling, we tend to be looking for elements around the very edges of the model, and that's where the sharpest magnetic fields happen. And so if you're using our vector hysteresis loss model in particular, getting good BH numbers around those corners is really what you want to calculate good loss values. So you can now apply a one-hit control called the edge cut, and so it will go and apply basically a single layer of inflation if you're a CFD person to every single edge, and it will recognize where the symmetry is and not apply it there. So that gives very good numbers for loss modeling. Moving into usability, everyone loves talking about the ANSYS cloud at the moment. For Maxwell, it's still in beta, so we're missing a few post-processing options, but on the whole, we use the same predefined machines as we do for HFSS, which tends to be on the RAM-heavy side and fewer cores. We use the same submission scheduler, so it's a case of logging into your cloud account, choosing ANSYS Cloud, and pushing OK. And then you can access all the post-processing while it solves, either through the web or through your phone. Anyone who's ever done variable speed work in motors or variable harmonic work in small transformers will know that for years and years and years we've wanted the ability to control the expression cache. And so this is a way that we can selectively pull out field data to save on memory. So we've always had the output formulas in for the time stepping. Now we can put them in for the expression cache. And so the net effect is if you change the rotating speed or the main harmonics you're interested in, it will adjust the fields that it saves to suit. That's been a very long time coming, so very grateful to see that. As of 2019 R1, we've gone and created a new license increment. So there used to be a license called the Maxwell 2D license. That's now merged into the Electromagnetics desktop 2D, and it comes with a few extra free products on the way. So it comes with the cable modeling cross-section tool. It comes with a full nonlinear version of Simplora. So that's minusing a few of the multi-physics bits of Twin Builder. You can use parametric studies without an optimetrics license. That's not a big deal. But if you have multiple 2D licenses, you can toggle it into solver mode rather than DSO mode. And that means you can run parallel studies without having to buy the optimetrics license. So that's quite a handy feature. If you're working heavily inside Workbench, and you want to be able to batch process Maxwell into the same, for example, static, structure, or fluent, you can now ask Workbench to create an optimetrics design, batch process out wherever the geometry sources, solve them all on one hit, and then feed them to RSN. So this is a case for, there are some companies in Europe who want to do 10,000 points with this system, and so now they can execute everything in batches and move through the Workbench process that way. This is just a nice feature which we just have always wanted. This is how we used to do post-processing. We never had the option to copy and paste the fields around. Mainly as a visualization tool, you can now toggle on all the field plots into full models. So this works for inductors, transformers, motors, anything with symmetry involved. If you've been here this morning, you have heard me mention the new optimizing tools. So we've previously had two groups of optimizers available in ANSYS. One was an optimetrics, one was a DX or Design Explorer. They're now merged, and you can access them all on the one GUI. And so this becomes our now entry-level optimization tool, and we use OptiStone, like Michael was talking about, as our sort of flagship. But that gives you quite a few more options to use. So moving into the Twin Builder, because I'm still on time. With digital twins, we've needed a new workflow because we often work with a big complicated multi-physics model, and then we need a way to deploy it so something like ThingWorks can grab a hold of it. And so the way that it works in Twin Builder is you can create your sheet, you then select the whole lot, go compile as a twin model, this collapses it down to a single .twin file, it gives you a block inside Twin Builder that looks like this, and then you can choose to either export it to something like ThingWorks, or you can copy and paste it to another twin schematic. And that twin schematic can then, you can run tests on it to make sure that your twin collapsed the way you expected it to. So that kind of closes the loop. And it supports almost all the blocks, except for a few of the native ones. But especially dynamic ROM, and the Modelica interfaces are fully supported. So it's probably about time we introduced our dynamic ROM tool. If you've ever done any ROM work inside Twin Builder to produce reduced order models, you'll know it's a fairly long, convoluted process because you have to understand how each ROM mechanic works. So the idea behind this tool is that we throw that in the bin. You bring in whatever data you've got, it can be from anywhere, We usually use .csv files at the moment, and you can choose which data you want to build and learn from. And so in this case, we've got an input power, and we've got a temperature somewhere. And we can learn from these, and then we can import other learning scenarios, which we can then either use as separate learning options, or we can use them as validation loops, so that you can build a ROM and test it against some more data, which you already had available to you. So once you've loaded these, it's just a matter of clicking build, and you can watch it as it converges to a final answer. So there are a few enhancements to the tools we have to do it. We have a nice new tab interface, which makes this a lot nicer to use. You can save multiple versions of your same ROM and compare them to find out which ones struggle with which scenarios. So for example, they'll left the accuracy cranked up on its first ROM, and it doesn't really struggle anywhere. But they've started peeling off layers of the ROM in these other versions, and they all struggle with scenario 4. So it might be a case of you come back and you change which bits you stripped out of the background. So Modelica has been a work in progress for about 2.5 years now. It's built on the model-on solvers, which is from a third party. And so inside Twin Builder, we've always had native a block schematic view, but we've never had support for the icons which come with a Modelica style library. And so now we have full support for that. Whenever you bring in custom models from anywhere, they always come in with the right variable names, the units, and the description associated with the pin. And you can pull up the description by mousing over the pin as well, because some of these custom icons aren't always clear what you're supposed to wire to which pins. So to access all the new features, they're all under the right-click menu. So if you right-click on them, the top 4 things here are where you find them all. In particular, getting shortcuts to the documentation is quite important because they tend to be a few pages deep. So that's a good fast shortcut for that. To anyone who's been using Twin Builder over the last 10 years, one of our pet peeves has been the fact that if you have these page ports to jump to a different page, you've got another system connected to it, when you delete the page port, it didn't rename this net. And so if you recompiled it, it was still connected. And so that caused a few frustrating errors until you worked out what happened. Now if you delete it, it renames it to something generic automatically, and that problem goes away. So with the whole move from Simplora to Twin Builder, we've had a new packaging set up, and it depends on what you want to use Twin Builder for as to what suits you. So I tend to work with systems and ROMs, but I don't really tend to deploy them, and so I end up in Twin Builder Pro and Twin Builder Premium. If you come to deploy them to ThingWorx, then you'll need at least one enterprise license, because that gives you the runtime generated element of it. And we also have direct access to some of the more complicated model or Modelica libraries, and they come as part of the Twin Builder connection. So in terms of what you can use Twin Builder with, there's a few platforms we've now got available. There's obviously PC ThingWorx, which we'll show this afternoon. GE Predicts has been around for a while, and SAP is the new one. So, footnote here, we're going to show this all live in the next room, in the next session, which will be soon. We have a PC ThingWorx digital twin set up, and it's connected to Twin Builder, and we show them both live and how you can use them for reliability type work.